I am De-Arteaga. I'm an assistant professor in the Information Risk and Operations Management Department at UT Austin. And today I'll be telling you about the gap between predictions and ML-informed decisions. And the work that I'll be presenting to you today is joint work with Alexandra Shodoshova, Ricardo Fogliatu, and Arthur Dubrovsky. And well, in recent years, we have seen an increase in the use of machine learning to assist experts in high-stakes settings. This includes healthcare, child welfare, hiring, but we still have a large focus on the predictive performance as the locus of evaluation. That's very clear to us from the machine learning perspective in how we evaluate algorithms, and it's also clear in how we often portray the wins and how the performance of algorithms is reported, right? So it's AI system is better than humans. AI just beat human doctors. But often in many domains, we don't care about doing better than the human necessarily, but we care about prediction-informed decisions. We care about whether human decisions, when assisted by an algorithm, become better. And so in today's talk, I'll be talking about two elements that are very important when we're thinking about this. The first one is the difference between predictions and decisions. And for this first portion of the talk, I'll be centering the human and how humans make use of algorithmic recommendations. And in particular, I'll be focused on the question, are humans capable of making good use of algorithmic recommendations to improve decisions? In the second part of the talk, I'll be focusing on the gap that exists between the construct that we measure and the construct that is relevant to human decisions. And for this second portion of the talk, I'll be much more focused on the algorithm. And the question that I'll be tackling is, how do we bring the constructs that we optimize for closer to the relevant constructs? So let's dive into the first portion of the talk, the gap between predictions and decisions. This is work that we presented at CHI in 2020. So this is the main HCI conference. And we've since done follow-up work in which we did a much more thorough empirical analysis. We also tackled some of the fairness questions associated to these that I'll be discussing. And we recently shared these as an SSRN working paper. So when we're talking about the gap between predictions and decisions and whether humans are capable of making good use of algorithmic recommendations, we can see this in the context of algorithm aversion and automation bias. Algorithm aversion and automation bias can be seen as two ends of a spectrum on how humans make use of algorithms or in general of technology that supports decision making. On one end of the spectrum, we have algorithm aversion that relates to undercompliance. And so these are cases in which the human says, well, I clearly know better than the algorithm, so I'm just going to dismiss it. I'm going to ignore this tool, and I'll just continue business as usual. On the other side of the spectrum, we have automation bias. This is a case of overcompliance. And one of the first domains in which this was identified was high-tech cockpits, where it was found that pilots were not as vigilant and not as likely to identify certain things as they would before because they became over-reliant on the high technology that was deployed. And so in this context, if we're using a predictive algorithm, this is a case in which we don't really get the benefits of human AI collaboration because the human is simply adhering to what the algorithm is recommending. So one way of refining this question is, are experts able to dismiss algorithmic recommendations when the tool misestimates risk? And so why am I talking about risk? Well, in a lot of cases, in high-stakes domains, algorithmic-assisted decision-making takes the form of risk assessment instruments. And so these are cases in which we're modeling the likelihood that a person or case will have poor outcomes. And this is what we have in the context of lending, criminal justice, healthcare, and the domain that I'll be talking about today, child welfare. So in child welfare in the US, it is estimated that 37.4% of children experience a child protective services investigation by the age of 18. And so for the stats of 2018, so that you get an idea, there's over 4 million referrals. Each referral may involve more than one kid. So each referral is a call to a child abuse hotline. And from these calls, there were investigations or alternative responses to 3.5 million children. So in Allegheny County, the county where Pittsburgh is located, the way that the child abuse hotline used to work was there was a call worker and they received a call of child neglect or maltreatment, and they were tasked with deciding whether the call was screened in for investigation. If the call is screened in for investigation, a social worker visits the home, and then there may be multiple responses and services offered to the family. And in an effort to reduce the likelihood of false negatives, of cases in which the call worker screened out a call that should have been screened in, historical records, so administrative information of the children and the family involved in a call, were also made available to the call worker. And as the information available grew and grew, that led agencies to turn to the question, can an algorithm tell when kids are in danger? And so in particular, they started working with a team that had deployed similar algorithms in New Zealand to build predictive models that could assist call workers in this decision. And some agencies are very optimistic that these can reduce the risk of false negatives. Some others have expressed a lot of concern. So you may be familiar with the book Automating Inequality. Virginia Uvent in this book dedicates a full chapter to the Allegheny County system. And the National Coalition for Child Protection Reform published a commentary titled Pittsburgh's Child Welfare Agency Goes Full Orwell. So what we're studying in this work is one of the pieces of the puzzle that we need to understand to better understand what are the opportunities and the risks of deploying these systems in this domain. So when the predictive model was deployed, the pipeline changed, and so the call workers still had access to the call, still had access to the historical records, and in addition to these, they had access to the output of a predictive model. The predictive model only observes the information, the historical information. It doesn't observe the information communicated in the call. And it provides a risk score from 1 to 20 and a screen approval flag, meaning in some cases, a supervisor needs to approve if the call worker wants to screen out a call. So in our analysis, we have data prior to deployment and data post-deployment, and neither of these overlaps with the data that was used to train the model. The model is trained to, there's actually two models. There's two outcomes of interest in the period of time that we're analyzing, and I'll go back to what are the outcomes that we consider in the second portion of the talk. There is the risk of out-of-home placement. This is whether the child is placed in foster care, and the likelihood of a future referral, of a future call associated to the same children. And as I said, these results in a risk score. So these probabilities are converted into ventiles, and then the maximum of these two is the score that is shown. And if the likelihood of out-of-home placement is greater or equal than 18, then there's a supervisor's approval screen out required, a supervisor's approval required for screen out. When the tool was deployed, there was a technical glitch that went unnoticed. So because of the way that the database was being queried, this meant that some features were miscalculated in real time, leading to misestimated scores. What we're seeing in this plot is the assessed score. So this is the correct in quotation score based on retrospectively calculated features. So if there hadn't been a technical glitch. And what was the score that was actually shown? we see that there's a very strong correlation, but 10% of shown scores were miscalculated by 5 or more points. And many cases that should have been flagged as mandatory screening weren't. So in this context, we asked 3 questions. The first one is, did the deployment of the tool impact co-workers' decisions? We can see this as a question of algorithm aversion. Did something change in the behavior? The second question is, did co-workers treat misestimated scores differently? Or did they indiscriminately adhere to recommendations? This is a question of automation bias. And is particularly relevant given that in other domains, such as criminal justice system, there has been some evidence found of automation bias. And also in the framework of other domains where these tools have been studied, there's an important question that is, how did the tool's deployment and co-workers' overrides impact racial and socioeconomic disparities? For example, in the criminal justice system, Alex Albright's work has found that non-uniform adherence to recommendations can exacerbate disparities. If people's likelihood to update their priors when they see an algorithmic score are different for different groups, that can exacerbate disparities. And so we asked, what happened in this context? To tackle these questions, we use regression analysis. And so we have assessed and shown score and assessed and shown mandatory flag. And so we have as dependent variable the co-workers screening decision, and we look at the interaction with deployment. We consider indicator variables for whether the score was overestimated or whether there was a mandatory flag that it shouldn't have been there. And similarly, whether the score was underestimated, analogous for the flag. And we have fixed effects for month, co-worker, and allegation type. And so these just controls for the fact that in the summer, calls may be very different than during the school year. Different co-workers may have different behaviors, and depending on the allegation type, the response may be different. So with these, let's tackle the first question, that is, did the deployment of the tool impact co-workers' decisions? And so what we see here is the relationship between the assessed score and screening before and after deployment. And so what we see here, especially when we look at the plot on the right, is that calls that had mandatory flags, and importantly, because the glitch was non-random, we cannot retrospectively calculate the shown score. This is why we do it with respect to the assessed score. We see that those that have a mandatory flag did become much more likely to be screened in. When we look at the regression analysis, and I'm just going to give you a little glimpse of the results. If you're interested in this, I really encourage you to look at the journal version, the SSRN working paper. But I'll give you a glimpse of what were the results that we found for each of these 3 questions. So when we look at the interaction between the mandatory flag and deployment, we find that the deployment of the tool did impact co-workers' decisions, which became better aligned with the score. This is a very unsurprising result that says, yes, we deployed this tool, we changed the way that co-workers were asked to make decisions, and something did change. But it is fundamental to be able to analyze the subsequent questions, because if we find that co-workers were more likely to dismiss misestimated scores, well, we need to make sure that it's not just because they're ignoring all scores altogether, right? And so this is what we find. The first portion is just, well, something did change. But then, was it different when the score was misestimated than when it was correctly estimated? And here, what we're seeing is the assessed score into buckets of whether it was underestimated, correctly estimated, or overestimated. And so what we should see is that if there's automation bias, then for the same assessed score, if it is overestimated, we should see an increase in screening rates. And if it is underestimated, we should see it lower. This is exactly the opposite of what we're seeing here. And to understand this, it's important to remember the non-random nature of the glitch, which means that cases for which the score was underestimated may actually be different in some ways. But the important thing to note here is that these different treatment of underestimated cases indicates that call workers are not relying on the information communicated in the call alone. And instead, they're able to avoid errors of omission, meaning errors in which they omit a case that requires action because they over-rely on the score. And we confirm this through the regression analysis. So let me jump here. Here we first look at whether there's automation bias. I'm gonna keep this result because it requires us to delve a little bit deeper, but to give you a glimpse of these, we show that there's some possible indication of automation bias that cannot be concluded for scores that are overestimated. But we do find that call workers avoid errors of omission. And when we look at an analogous regression, same model specification, changing the dependent variable for whether the case is accepted for service that serves as a validation of the coworker's decision, then we see that these are indeed more likely to be accepted for service, suggesting that there is a warranted screening. So to summarize, for the second question, what we find is that even though the deployment of the tool did change how co-workers were making decisions, we find very strong evidence that they avoid errors of omission. And finally, for question 3, how did the deployment of co-workers, how did the deployment of the tool and co-workers overrides impact racial and socioeconomic disparities? I'll show you the results for racial disparities. We see that when we look at the likelihood of screening, this is just in whether the case was screened in, not controlling for any confounders or anything like that. We see that prior to the deployment of the tool, cases where at least one of the children involved in the call was Black were more likely to result in a screening. And after the deployment of the tool, the disparity remained the same. When we look at the algorithm in isolation, if what we were doing was saying, let's keep the same rate of screening overall, so let's screen in the highest scoring cases according to the algorithm, this disparity would have grown significantly. To be clear, this does not necessarily mean that this constitutes a form of discrimination in that we don't know whether these calls required screening, but it is fundamental to understand how both the goods and burdens associated to the child welfare system are being allocated. Because an important thing here is that when a child protective services investigation is open, a lot of burden is placed on the family. So we have costs on both sides, right? There's a cost of missing an investigation where the child was at risk and needed support. And there's also a cost of having false negatives and disproportionately burdening families. So here, the interesting thing is that when we look at rates, we see that both the human and the algorithm have a higher likelihood to screen in cases where at least one of the children is Black, but when we combine them, we don't observe a compounding effect. And what we see actually is that the human in the loop reduces the disparity that would have been introduced by the algorithm. So the question is, well, why is this happening? So to tackle this, we turn to the regression analysis, same model specification, but including interactions with a protected attribute. And here I'll show you the results for race. And what we find is that, confirming what we just saw, Black children were more likely to be screened in prior to deployment. But we find that there are no significant interactions between the protected attribute and the score, the mandatory flag. What does this mean? It means that the deployment did not have a differential impact on screening rates, meaning the coworker's likelihood to adhere to algorithmic recommendations did not depend on the child's race. And so what this suggests is that this reduction in the difference in screening rates when you incorporate a human in the loop is not driven by a different likelihood to adhere to a score conditioned on the child's race, but rather it's because call workers are integrating unobservables into their decisions, very likely the information communicated in the call. And so that means that the distribution of the scores of the cases that are screened in is different, meaning and this is connected to what we saw in the second question, that is call workers screening cases where the score is lower, likely making use of unobservables, information communicated in the call, and that reduces the difference in screening rate that we would observe if the algorithm was making autonomous decisions, which, to be clear, is not a question that is on the table, but it allows us to analyze the role of the human in the loop, right? And so to summarize, what we found is that coworkers' decisions became more aligned with algorithmic assessments after deployment of the tool, but they did avoid errors of omission, performing corrective overrides. This is a term that we've given to cases in which the human in the loop dismisses the algorithmic recommendation. And in this case, we particularly see it when the tool underestimates risk. And we find that the deployment of the tool did not affect disparities in screening rates overall. The likelihood to override recommendations did not vary across protected groups, but a human in the loop did lead to smaller disparities than the algorithm alone. And I'm going to pause for a moment to see if there's any questions of this first part of the talk before I dive into the second part.
Hi, Maria. It's not unusual that you don't have questions because usually we do the whole talk and then people ask questions. So, but I mean, to everyone.
Then we can stick to that. Yeah.
Yeah.
Whatever is your usual convention. Perfect.
Please interrupt Maria, and then she will be happy to answer. Thank you.
And well, now that we've seen the difference between what we think when we're thinking about predictions and decisions and the role of the human in the loop. And one of the important things that I'll mention here is that this result is quite different to what has been observed in other domains when it has been shown that there's a high risk of automation bias, for example. And so what this shows is that things can really go in both directions, right? Like the human in the loop can add value or they may not. And so one of the big questions right now is how do we design for productive human-AI collaboration? And in the second part, I want to give you a brief overview of some work that we've done looking at the gaps between the construct that we optimize for and the constructs that we care about. This is part of a working paper that it won the Best Paper Runner-Up Award at WITS last year, and you can find the preprint on arXiv. So typically in domains such as child welfare, but this is common across many decision support contexts, the data generating process has a human mediator. And so what that means is that we have a selective labels problem in which we only observe the cases in context, but also what we observe is not directly what we care about. So typically the standard machine learning training is we dismiss the information that the human produces and we just say, okay, we have our covariates, we have the observed outcome, and we have an algorithm for training. The challenge here, in addition to the selective labels problem, is what we term the construct gap. The fact that we have a measurable but flawed proxy. In the context of child welfare, this means that what we care about when making screening decisions is whether the child is at risk, but what is being estimated is the probability of out-of-home placement. And here I'll make a small parenthesis to mention that even though in the first portion of the talk we were looking at both out-of-home placement and re-referral, the agency has since moved away from re-referral because they deemed it to not be indicative of risk. And so typically we think of the human in the process as this inconvenient meddler in our data generating process. And typically we say, okay, how can we reconstruct why? And so, for instance, we use sampling bias correction methods so that we get rid of the effect introduced by this human meddler. What we propose is to reframe these and look at the fact that there's a wealth of discarded, noisy expertise that is contained in the decisions of the humans that mediate our observed outcome. And so the question is, can we learn from experts' decisions to bridge the construct gap? And in our work, we also look at how these can help address some of the challenges of the selective labels problem, and in particular, the violation of the positivity assumption. And so another way of framing this question is, can we learn from experts' decisions whenever they display certainty and consistency and learn from observed outcomes otherwise? Why learn from expert consistency? Well, expert knowledge is often sufficient to correctly and consistently assess a subset of cases while not being sufficient for others. We can think of that in the context of healthcare. It is often the case that physicians can do a really good job at diagnosing a subset of patients very confidently because their symptoms are very well known, or whatever information we have to date, whatever scientific knowledge we have, is enough to very confidently assess a subset of cases where there may be a lot of uncertainty for other cases. And a similar thing may happen in child abuse hotline cases, where operators may be able to identify a subset of cases that definitely warrant a house visit, while being more uncertain about others. The question then is, or our approach is, well, let's learn from experts' decisions whenever they display certainty and consistency, and learn from observed outcomes otherwise. The question, though, is how do we do this? Naturally, many of you may have already seen this connection of this is very similar to what we do when we learn from wisdom of the crowds, where we're learning from consistency. But it's very different to do this when we can query multiple humans and then directly estimate consistency than when we have historical data generated such that there's a single expert that assesses each case, and when it is extremely hard, expensive, or simply unfeasible to generate data where multiple experts assess each case because their expertise and time are very limited. And so when we only have one expert, how can we estimate consistency if we have a single expert per case and we have a non-random assignment between cases and experts? So for instance, which physician sees which patient may depend on elements such as geographic location, type of insurance that covers their service. Similarly, in the call workers case, who answers a call may depend on, do they work a night shift or a day shift? Do they work a weekend shift or a week shift? Is there a question? Okay, no. Okay, so our proposed approach is to model the human decisions using ML to first identify consistency, and then we leverage influence functions to identify whether consistency is across experts. And then we propose a label amalgamation approach to incorporate the inferred expert consistency. The core assumption here is that we want to learn from consistency. This is likely in cases where experts' decisions encode knowledge, but naturally in cases where consistency is a result of shared biases, these may not be desirable. So this is an important assumption to consider before using this method. And we think of it primarily as a first step in the direction of bridging the construct gap. So we have our data of, we have covariates, we have human decisions, and we have observed outcomes, likely with a selective labels problem. And we can first train a model to predict the human decisions. And if this is a calibrated model, then we can obtain a high consistency set. So if we let delta here be something like 0.05, then these are cases where we have very high confidence in our predictions. The question though is, well, are these high probability predictions reflective of consistency across experts? This is non-trivial if we have a non-random assignment of experts to cases. We can reframe this as asking, are high probability predictions influenced by historical decisions of multiple experts? To answer this, we turn to influence functions, which is a technique from robust statistics that allows to estimate how functional, so it may be the loss function, it may be the predicted probability for a case, will vary if we perturb the weights that we give to our training data in a certain direction. So we can think of the default being all our training points receive a weight of 1. And we can make perturbations of the weights we give to the training data and then look at how is it that the curvature of the whatever functional we care about at a given point would change. And in particular, we can say, well, what happens if we perturb the weights such that we give more importance to the instances labeled by one expert? And so what this allows us to estimate is how will the estimate of our predicted probability vary if the importance given to expert H is perturbed by epsilon. And the important thing to know here is that we can estimate this, right? So here we're looking at the gradient of the predicted probability as we vary epsilon. And the only part that is a little bit computationally expensive is the inverse of the Hessian, but we can estimate it in efficient ways. And so with this, we can, and here I'm going to skip a couple of the details, but we can revisit our high consistency set, right? So that we don't just have the high probability predictions, but we look at whether, based on functionals of the influence across experts, whether these are driven by many decision makers. And so this is our new high consistency set. And so with these, we can now turn to the results. That is, when we're measuring algorithmic performance, we typically focus on observables. So in the case of child welfare, if we look at out-of-home placement, and we look at the precision, and this is looking at the top 25% highest scored screening cases, we see that if we train a model to predict out-of-home placement directly, it does so much better than the model that is trained to predict the human decisions. The challenge here is that we, as I said, we don't just care about out-of-home placement. And there's other outcomes, such as whether services are offered to the family and whether a call is substantiated, that the agency has chosen not to use them as predictive outcomes because there's out-of-home placement provides a validation that comes from an external agency, but these other outcomes allow us to look at whether other outcomes of interest are captured or not by a model that predicts out-of-home placement alone. And this is particularly relevant because there are cases that do not require an out-of-home placement, but where services offered to the family can improve the well-being of the child and especially reduce the risk of a future out-of-home placement. And so when we look at these, we see that if we see these as unobserved outcomes here, the human is actually doing a lot better in terms of services and substantiation of calls. And so we see that there's these other dimensions of importance to the human decision that the model trained on out-of-home placement alone is not capturing. When we incorporate expert consistency by our proposed approach, the one that is most relevant for you to look at is the orange one. Here we see that we're able to retain very high performance with respect to the observed outcome, with respect to out-of-home placement, but we also get the benefits of having incorporated information from the human. And so we do a lot better than the algorithm that is trained on out-of-home placement alone. And here we're also learning, comparing with learning to the first, that is the closest framework in terms of trying to combine both humans and algorithms. And so to summarize, what we see is that there are high-risk cases whose risk is considered by the experts, but is not captured in the target labels used to train a deployed model. And on the methodology side, we've showed that leveraging inferred expert consistency can allow us to build models that mitigate the risk of omitted payout bias and help us bridge the construct gap. And so to wrap it up, when I talk about minding the gap, there's two elements here that we've discussed. First, the gap between predictions and decisions. How humans make use of recommendations matters and varies. And while algorithm aversion and automation bias are phenomena that are real and we should be concerned about, this doesn't mean that humans always make poor use of algorithmic recommendations. And so a central question right now in human-AI collaboration is, how do we design both the algorithm and the socio-technical system so that we obtain productive human-AI collaboration, in which both the algorithm and the human are contributing to improving the decisions. And it's also important to note that when we choose a proxy, that is what we're optimizing for, typically this proxy is convenient, but it's not the construct that we care about. And when we're evaluating with respect to it, we may be missing important elements. In particular, if we're comparing how is it that the human and the algorithm are doing, well, it may be that the human is not just optimizing for that what the algorithm is optimizing for. And so in defining ML for decision support, we need to center the relevant construct, and I have shown one approach that can help us use different sources of information to bridge the construct gap. And with this, I'll wrap it up and open it for questions. Thank you very much, everyone.